Textbook definition of boiling point is a temperature where the vapor pressure of a liquid is equal to atmospheric pressure. Let's look initially at this blue liquid. Above the blue liquid, there's going to be a few particles of that substance in the gas phase, and the pressure due to these gas phase particles is its vapor pressure. As the temperature increases, there's going to be a greater number of particles that can escape into the gas phase because the average kinetic energy of these particles increases. So if we look at a graph of the vapor pressure versus temperature for the blue liquid, we would see it would slowly increase upwards. Let's say that our atmospheric pressure is this pressure right here. We can draw a line over, and we can see that at this point, the vapor pressure of the gas is equal to the atmospheric pressure. If we draw a normal line down, we can determine the boiling point of that liquid. Let's consider the situation of this green liquid, and let's just suppose that this green liquid has weaker IMFs than the blue liquid. And that means that at a given temperature, it's going to have a greater number of gas phase particles. So at the initial temperature, it's going to have a few more than the blue did, and it's still going to increase the number of particles as the temperature is increased. However, it's going to increase more rapidly. So we could draw a line corresponding to the green liquid as so. And here is a point at which the vapor pressure of the green liquid is equal to the atmospheric pressure. And we would see that its boiling point is lower than the liquid that has stronger intermolecular forces. So what we can conclude from here is that if we have an increase in IMFs, we're going to increase the boiling point. The statement of the question is asserting that helium here has the lowest boiling point, and they're going to increase until they reach xenon, which is the highest boiling point. Now these are all atomic, and the only IMF present is London dispersion forces. Okay, London dispersion forces arrives out of induced temporary dipoles Induced temporary dipoles become stronger as the electron cloud gets larger. This is due to an increase in polarizability. So actually ranking these atoms with respect to their size is also ranking with respect to their boiling point. And as we go from helium all the way down to xenon in the periodic table, we see that we are increasing the number of electrons, and therefore we're going to be increasing the London dispersion forces, and that's going to have a corresponding increase in boiling point.